what kinds of decisions should your planner generate in order to either interact with the humans or to control the agents that it is responsible for, so the robot or whoever it is. Okay? And this decision support part is basically split up into three parts. The first I'll talk about when you have explicit constraints on your planning process, and I'll elucidate the nature of those constraints in the next part of the presentation. There's also a part on implicit constraints, dealing with the unspecified preferences of humans. Your planner needs to deal with that sometimes. So Rao will deal with that, and then we'll also talk a little bit about incomplete dynamics. So what happens when you don't fully know what are the actions in the world and so on. Okay. So the first part where you talk about explicit constraints, I will actually demonstrate this in the context of this continual planning and replanning problem. Okay. So this is essentially a problem where in any human-in-the-loop planning scenario, right, you have new information that's coming in all the time. Okay. This information could either come from the sensors on your agent, right? So if you're thinking about a human-robot teaming scenario, your agent could basically be equipped with a bunch of sensors that are sending you new information, which force you to replan. It could also come from other agents, right? So if you think about something like planning for crowdsourcing, where you have many different agents, you have many different humans who are doing this crowd planning process for you. When they give you new information, your planner might need to update its plan that's currently executing. You might get new goals from either humans or from other agents, okay? And what happens then is, so think about the plan generation process, okay? Your planner basically generates a plan first, okay? The moment your planner publicizes that plan, okay, you're producing commitments in the world based on that particular plan. So think about, as a human, when you make plans to say fly out to AAA, right? And then you tell people about your plans to come to AAA, and obviously there are people that you know who might want to meet with you. So they say, okay, let's have lunch, on Sunday afternoon, or let's have dinner on Monday evening, and so on. So these are extraneous commitments that are being produced by other agents, for example, once you publicize your own plan, okay? And now what happens is, if you happen to change your plan, suppose you have to replan, okay? So suppose it turns out that you couldn't come to AAAI because there was a snowstorm, right? Now it's not just your plan that changes, but also the commitments that are induced because you publicize your plan to other agents. And in this work, continual planning while respecting commitments, I'm going to talk a little bit about how to essentially do that, okay? So to ground this in a human-in-the-loop planning problem, think about this following human-robot teaming scenario, right? So think about automated warehouses. So in fact, after we thought of this example, it turned out that Amazon actually is doing something that's very similar to this. So Amazon has these huge warehouses, right, which need to be managed. Now they can't do it in a fully automated fashion because they have to have at least one human, for oversight on these things. This is like Rao was saying, right? You need at least one human who is in charge of the decision processes, okay? But obviously you can't hire humans for everything, so you try to automate some of it. So Amazon does this, it's actually Kiva Systems that does this for Amazon, where they have these huge warehouses, and I'll show you an illustration soon. So the only human on the floor, almost usually always, is a packager, okay? So there's one guy who's standing in a corner of the warehouse, and this is the person who is issuing commands and goals and orders, and this is the person who is the last step of checking, right? So if you put together an Amazon box that is going to go out for delivery, this is the person who makes sure that everything is fine before it's actually sent off, okay? So that's the only human in the entire process, and that human issues goals to the robots, okay? And your robots are these little Kiva robots, these orange things. I don't know how many of you have seen visualizations of these Kiva robots. They're these little orange robots that can basically go from shelf to shelf in these huge warehouses, and they can transport items on shelves to the packager, who then puts them together and ships them out to you. And the goals are basically the order requests which come in dynamically. Okay, so it's not that you start with a set of goals and those are all the goals you have. Your goals keep changing. Orders come in, orders get cancelled. A particular order has things added to it, things removed from it, and so on. Sometimes you go to a shelf and you find out that you're out of an item, right? Then you need to figure out what else to do about it and so on. So there are lots of things that can go wrong. So to give you an example, this is of course a very simplified layout of this whole Kiva robot planning thing, right? Which is that you have a warehouse layout, okay? And like I said, you have a human who is usually the only human in the entire process, right? So you have a human at the end of the warehouse to whom the packages are being delivered. Okay, so that's your overall goal, that you need to deliver certain packages to the human. And then you have these orange things, which are the Kiva robots essentially. Okay, and the robots can navigate this warehouse, which is basically, think of it as a grid basically. Okay, and there are certain locations on this grid that give you access to shelves, and shelves have packages on them. So these robots, what they can essentially do is go to a particular shelf, get a package off of that shelf, and then bring it to you. And again, this is a simplification of the warehouse scenario, but that's essentially what you have. So you have agents, which are basically your transports or your Kiva robots, right? And you might also have, for example, tow trucks if a robot breaks down in the middle, because these are huge places, these warehouses, right? And there's a lot of automation and things are going on and things might break down and so on. So what are some examples of things that might go wrong? We call them perturbations, right? Because if you need to replan, why would you need to replan? It's because things can go wrong in the world, okay? So what are some examples of things that can go wrong? So for example, your transports, your Kiva robots can break down, okay, in the middle of performing a particular task. So not only do they stop performing their task, they might also be blocking the way for other robots, for example, okay? So you need things like tow trucks and you need garages to fix them and so on, okay? You can also have packages that fall off of these robots, right? Because these Kiva robots are pretty simple robots. So you might, while they're moving, you might have packages that fall off, right? So then you need to go back and get another package to replace the package in that order and so on. And so there are many different things that could go wrong like that, okay? And the commitments that I'm talking about, so remember this notion of commitments, which I'll keep coming back to, was this idea that if you initially had a plan in your warehouse, right, and something goes wrong, then what are the commitments that that plan produced, okay? So examples of commitments in this scenario, and commitments are usually always between, they're from agent to agent. So that, a commitment is between two particular agents. In this case, your transport or your Kiva robot might have a commitment on holding a particular package. So it might have said, okay, I'm going to go and get that package, okay? And if it breaks down, that's going to affect that. You might have tow trucks that commit to towing transports that break down, okay? So suppose this guy broke down, then this tow truck might actually say, okay, I'll come pick you up and take you to the garage to fix you, okay? You can also have commitments on packages being delivered to the packager, okay? So a particular transport can promise to this packager that I will get this package for you, okay? So and if things go wrong, some of these commitments get affected, and the whole problem that we're going to be looking at here is replanning in the face of these commitments. So how do you honor some of these commitments when replanning is necessitated, okay? So there are many different theories of how to replan, and again, replanning has seen a lot of study in the automated planning community. One of these theories is to just abandon the previous plan, okay, completely. Just come up with a completely new plan, okay? So abandoning the previous plan is one way to replan. Another way to replan is to reuse as much of the previous plan as possible, okay? So the idea behind this is that obviously you expended some effort in coming up with the initial plan, okay? So maybe you want to reuse as much of that initial plan as possible in order to come up with the new plan, okay? So reuse parts of the original plan to produce a new plan. And then finally, the third notion, which I will be expanding on here in this particular presentation, is this notion of commitment from the previous plan, okay? So instead of being beholden to just some notion of form, like instead of being beholden and saying, the previous plan looked like this, okay? Or instead of throwing out the previous plan completely, you look at it in a more causal manner. So you say, what is it that the previous plan was achieving, or what was it promising? So those are the commitments that I'm talking about, okay? And what you have essentially is that if these commitments are between agents, so you have a multi-agent problem, okay, because these commitments are between agents, and you are reducing that inter-agent replanning problem, you are scoping it down to an intra-agent problem, okay? So if you are the agent that is doing the planning, okay, and something goes wrong in your world, and you have to replan, then you think of all the other agents that might possibly be affected by you changing your plan. Like, what are the commitments in the world that you are going to break by changing this plan, and can I actually retain some of those commitments? So that is commitment sensitive replanning, okay? That considers commitments from previous plans. So we are going to talk a little bit about that, and so I want you to remember those three ways of replanning in the context of examples such as these. And associated with those 3 different ways to replan, there are different replanning constraints, okay? So remember I said the first way to replan is to just abandon your old plan. If you completely abandon your old plan, then it's unconstrained replanning. There are no constraints from the previous plan because you're completely abandoning it, okay? There is also similarity constraint replanning. So if this is the second type of replanning, right? That if you want to preserve or if you want to reuse some of the information from the previous plan, ways to do that are to, for example, do action similarity, right? So you say that I want my old plan and my new plan to be as similar as possible, or to, to minimize the number of actions in which the old plan and the new plan differ, okay? So this is a notion of action similarity. There's another notion of causal similarity, right? So if you think about plans, plans can be seen as sequences of actions, okay? A plan is a sequence of actions, or they can also be seen, these actions, they have causal links between them, okay? So action A is providing a particular precondition to action B, okay? Now that precondition is a causal link between action A and action B, okay? So instead of looking at just the names of actions, you can look at the causal links between actions, okay? And in any case, you can try to minimize the differences between the 2 plans. And then finally, the third way of replanning is this notion of commitment constraint replanning, okay? So you try to look at what are the dependencies between various agents' plans, or the actions that various agents are executing, okay? And then you project those commitments between these different agents into a new replanning problem, so that when the agent is replanning, it tries to preserve as many of these commitments as possible. So the agent is docked a penalty for violating a commitment, for every commitment that it violates, okay? Now, going with this theme of 3s, right? So there are 3 ways to solve the replanning problem. There are 3 different constraints associated with them. And so obviously there are 3 solution techniques, okay? So one idea is basically to just use, classical planning, which is just, existing planning algorithms. You solve it. So you have an initial problem instance I and G. I is your initial state, G is your goal state, okay? And your problem changes from that to I prime, G prime, okay? So I prime is the new state of the world, something changed in the world obviously, okay? And then G prime is possibly a new set of goals, okay? So these are new goals that your agents are trying to achieve. And so you try to solve that new problem using a classical off-the-shelf planner, okay? So this is the way to replan where you completely abandon the old plan. You're not caring about what was in the old plan, alright? The second way is to use specialized replanning techniques. So this second solution technique for replanning, it corresponds to where you want to reuse as much information from the previous plan as possible, or you want to preserve as much similarity with the previous plan as possible. So you might do things like, for example, local search, right? You can do iterative plan repair. So you can say, here's the old plan, and this old plan obviously broke for some reason, okay? So can I start at the point that it broke, and can I try to iteratively repair that plan, keeping it as similar as possible to the old plan, okay? So there's some techniques like that. And then here I'm going to talk about this notion of compilation to partial satisfaction planning, which I'll explain in the coming slides. So the idea here is that the commitments, remember the commitments that we were talking about, what are the commitments that are generated, by the publication of a plan in the world? You try to model these commitments as constraints on the replanning process, okay? So you say that when I'm producing a new plan, when I'm replanning, okay, it's not just the planning problem anymore, but there's also these other extraneous constraints that are coming because I have to preserve the commitments that my previous plan was making, okay? So we'll talk a little bit about that. And before I move on, I just want to flash this picture of a generalized notion of replanning, okay? Since we're talking about replanning and decision support when humans are in the loop, okay? So here you will see that you have the planner, okay? And ostensibly the planner is supporting some agent. You can think of a robot here, you can think of some other smart program, whatever it is, okay? That the planner is supporting. And what happens is that your planner gets an initial state and a goal description. This is your problem statement basically, okay? The planner gets that as input and produces a plan, okay? Now obviously there are many different things that can happen once the planner produces a plan, okay? The first thing of course is that the plan is sent off for execution, okay? But in some particular scenarios, before you're able to send the plan for execution, you might have to get it signed off by some humans, right? So remember the NASA scenarios that Rao was talking about, where you might still have an automated system that produces a plan for you, but you need a human to sign off on that plan. You need maybe a mission commander or a mission validator to sign off on that plan and say that, okay, this plan looks fine, right? So you might need to present it to a human for assessment, okay? At the same time, if you're dealing with a multi-agent scenario, right? If you're in some multi-agent application or in a multi-agent world, then you might want to publicize your plan to the other agents before sending it off to execution. So we're thinking about cooperative scenarios over here, right? So you have multiple agents creating plans at once, you might want to send your plan out to other agents. So regardless of what you do, you eventually then end up sending your plan for execution into the world, okay? And then what happens is that something goes wrong in the world. There's a sensing event and you figure out that something broke in the world. So my old plan, this plan that I generated, is no longer valid, okay? What do I do now? So this is where all those different kinds of replanning come together, the 3 different types of replanning that I was talking about, okay? So what happens is when something goes wrong, you monitor, you have an execution monitoring system, ostensibly, that determines what's wrong with the world, okay? Why will your old plan not work anymore, okay? At the same time, you also have some constraints that are produced, okay? And these are the constraints that we were talking about. So for example, if you had shown your old plan to a human for them to sign off on, okay? Then there are some constraints saying that, okay, maybe you want to preserve similarity to the old plan. This is similar to what Rao was saying about if you do some annotations on a particular piece of paper or on something you're reading, and then you send it back and you completely change it again, right? Then there's a lot of effort that the human, in this particular case, will have to spend just on getting the context back for that, okay? So instead of doing that, you might want to preserve some notion of similarity to your old plan, okay? Similarly, when you've shown the plan to other agents, if you want to change it, there are some commitments on changing that plan, right? Because these other agents might have made some commitments on your plan. So you might want to take them into account as well. So that's sort of a generalized notion of replanning. And again, this slide just sort of summarizes the constraints that we were talking about, right? So these are all the different constraints that you have on replanning as a problem. And then corresponding to that were the 3 solution techniques that we talked about, okay? So if you have replanning as restart, which is you just abandon the previous plan, then you just use classical planning and solve the new instance, the new problem instance. If you have replanning as reuse, then you do local search approaches. So you basically start from the plan that failed, you start from the old plan, and then you try to minimize the differences with that plan while finding a new plan that will work in this new state of the world, okay? And finally, you have replanning to keep commitments. So what happens here is that you think of commitments as constraints on your plan generation process. So you think of them almost as additional goals, okay? So the planner has certain goals that it's trying to achieve, but then you also have some additional goals now, which are these commitments that you have to keep, okay? So think of these in terms of the example that I was giving you, right? With the warehouses and all of that, right? So some of your commitments might be, I need to get this package to the packager, okay? Now if this particular transport broke down, maybe you can put some other transport on the job, okay? And so on, things like that. So those are commitments. And I mean, some of this work is motivated by this realization that all plans are essentially made up of commitments, right? So you have causal commitments in plans. So if you think of a plan as a sequence of actions, right? The action that comes immediately before the next action, it's committing to give certain preconditions to that action. So that's a causal commitment, right? And you might also have multi-agent plans where agents, if they're all acting in the same world, they either enable or disable conditions for the other agent. So there are commitments between agents with respect to that as well. And commitments can be thought of as goals, right? So you can add them as additional constraints on the planning process, okay? And that's essentially what we wind up doing here. Now, one advantage of reasoning about the replanning process in terms of commitments is that you can basically define it in terms of metrics, okay? So now you can start thinking about, here are various candidates for the replan, okay? So my old plan broke, and here are many different plan candidates that I can come up with when I'm replanning. How do I rank these candidates, okay? Is there a metric that will allow me to rank these various candidates? And so it's useful to think of commitments in that particular case, because you can think of these replans as breaking commitments, okay? And you want to maybe take the plan that breaks the least number of these commitments, or it minimizes some notion of, commitment sensitivity, okay? And obviously, in order to come up with that metric, you need a notion of what it means to break a commitment, okay? So if you break a commitment, are you assessed some penalty, okay? Similarly, if you keep a particular commitment, do you get some reward instead, okay? So if you preserve some commitment with the old plan, do you get some reward, okay? So you might get a reward R for fulfilling a commitment and a penalty P for violating it, right? And this, you can think of this in terms of if you have multiple agents and the agent that you're planning for, it basically engenders a bunch of commitments because it publicized its plan. Then when it tries to make a new plan, are there values, are there reward and penalty values on breaking these commitments or on keeping these commitments? Okay. Now, one non-trivial question obviously is how do you set values for these rewards and penalties? So for agent-based commitments, you can actually try to get these values from real-world applications, right? So for example, NASA has estimates on how valuable certain windows are, right? So you have observation windows, okay? And you have estimates on how, if you lose this window, how much time is it going to be before you get another window to observe the same kind of phenomenon and so on, okay? So you can actually set values on how, on what penalties or rewards you get on satisfying these commitments. And then for similarity-based approaches, where you're trying to maximize the similarity with the previous plan when you're replanning, right? You can say that for every different action that I have from the previous plan, I'm going to assess you a penalty, okay? So if my old plan and new plan differ, say in 4 places, then I'm going to have 4 times that penalty unit, okay? So you can put it in terms of that. And one of our contributions in this work was basically to come up with a way of compiling some of these replanning techniques to something known as partial satisfaction planning, okay? So partial satisfaction planning is essentially, it's a technique where basically you think of, so you have planning goals, okay? Your goals are no longer hard goals, you think of them as soft goals, okay? So your plan need not necessarily achieve all of the goals that are part of the planning process, okay? If you achieve a goal, you get a reward R, and if you don't achieve it, you get a penalty P, okay? So it's almost like you're relaxing the notion of goal, okay? So that's partial satisfaction planning, and we basically had a technique to compile action similarity and causal link similarity. So various ways of replanning, how do you compile them into, into a partial satisfaction planning problem? I'm not going to go through all of this, but there is work that exists on this. So this is essentially the idea where you can think of the replanning problem as planning subject to a certain set of constraints. Okay, in this case, the constraints that I was talking about were either similarity constraints or they are commitment constraints, right, to other agents, to the plan that you publicized. Okay, and so those are the constraints that we were talking about. But you can also have a notion of interaction constraints. So this is that work that Rao was mentioning in the introduction on Grandpa hates robots, right? So you can think easily, right? So instead of thinking about a multi-agent scenario like the Amazon warehouse, right? Think about a human-robot interaction scenario where instead of teaming together, your robot is trying to actively avoid humans, okay? Because it knows that humans don't necessarily like being around it, okay? So in such scenarios, what you can do is you can define certain conditions, okay? Certain constraints, certain interaction constraints that basically constrain the plans that the robot is able to come up with, okay? So you say things like, don't enter the bathroom while it's occupied, okay? Or don't vacuum in a particular room while I'm reading, okay? So these are now constraints that eliminate some of the possible plans that your planner could come up with for the robot, okay? And so, there are many different examples of this, and I'm not going to go into details of what this does, but there is now work on considering these explicit constraints. Once you name these constraints, okay, how does your planning process change in order to take these constraints into account? So this part was basically about explicit named constraints, okay? So think about interaction constraints in this Grandpa hates robots work, or you think about commitment constraints when you're replanning in the continual planning work, okay? But there's also a way of taking implicit preferences and constraints into account, and Rao's going to talk about that part now, where he talks about taking a notion of implicit constraint. So if you're not told that this is a particular constraint that needs to be respected while planning, but you can figure it out based on showing plans to humans, for example, how do you deal with that? So, Rao, do you want to?
So with any luck, this would be the last, one more change, and that's it, and then we'll be fine, hopefully. So anyway, as Karthik said, I'm going to talk a little about how to handle the incomplete models. And the models can be about constraints, the preferences of the human, as well as the dynamics. As a kind of a recap of what we have been doing until now, you notice that we have mostly used until now the existing planning techniques and sort of to the challenges of human-in-the-loop planning. So for example, he looked at how to use plan recognition techniques for doing the interpretation, and then he also looked at how to use the partial satisfaction planning and replanning to support continual planning, and what are the ways in which they have to change. This other part that I'm just about to talk about is basically what happens when you have incomplete models, and normally the traditional planning techniques don't actually look at incomplete preferences and dynamics. So in some sense, this is stuff that we've been doing that, it is connected to planning techniques, but it's also sort of a different problem solution concept. So that, it'll take a little bit of getting used to. So basically, as the traditional line in classical planning has been, start with the classical planning and keep making the problem more expressive. So introduce stochastic dynamics, introduce temporal dynamics, introduce metric quantities and so on. And what we are looking at right now in this part of the talk, as I have already motivated in earlier on, is basically you want to consider what happens to planning problem when the preference information and the dynamic information is incomplete. Okay, so that's what we want to look at, and so we've been looking at this as a model-light planning. That means the models are incomplete, and then so it has uses in places outside of human-in-the-loop planning, but it also has significant use within the human-in-the-loop planning, because as I mentioned, many cases there would be incomplete models in the human-in-the-loop planning. Okay, and this was something that I was mentioning that that the planner in the context of human-in-the-loop planning will likely have an incomplete model is something that people have recognized even in the beginning times, even in the 90s when they were looking at mixed initiative planning. So this was actually a sort of an excerpt from Allen's paper on trains, where he basically says, look, we don't believe that planners will have complete models in, when you are humans and planners in the same loop. And so we are actually going to, even though the problem that we are looking at happens to be a map following for which you can get complete model, we will experiment with a planner which deliberately has lesser model, incomplete model. Okay, so that's sort of, it's not something that we suddenly recognized, it's just that not too much work was done at all in incomplete models. So that's what we're going to look at a little bit quickly today for this part. Okay, now whenever you have incompleteness, the first thing is, why don't we just learn? Why don't we wait until the model becomes complete? Then we can do the usual traditional planning. That's a reasonable temptation. But then that is kind of not a good answer, because you will always have incomplete models. At any given point of time, you will always have incomplete model of preferences and dynamics. Over a period of time, you might be able to improve your knowledge. So you should do learning, but you should also know what to do with the incomplete model that you currently have. Okay, so this part mostly is about what to do with the incomplete model you have, and I'm not saying you shouldn't learn, and there is actually a lot of work that we have done and other people have done on how to learn to improve models. We'll mention a little of it here, but my focus is on what matters, what does it mean to do planning with incomplete models. Okay, so here are some challenges for just handling incomplete models. One, of course, you need to sort of think of how do you circumscribe the incompleteness in the model. So for example, if I just give you a model and say it's incomplete, I have no idea why it's incomplete, then what can you do? You just use the plan model to come up with a plan, and you say it might work, it might not work, I have no idea. Okay, so the question of course is, if you can circumscribe the level of incompleteness in the model, sometimes you might be able to make more interesting guarantees. The other thing is, if there is incompleteness in the model, you will actually, the question of what is the solution for a planning problem changes. we'll notice that, for example, for incomplete preferences, we will start talking about a diverse set of options of plans. So you don't generate one plan, you generate multiple plans and present it to the user. And for incomplete dynamics, you will wind up talking about robust plans, which is basically the plans that might work irrespective of how the model becomes completed. Okay, and then of course, as I said, you can always eventually also depend on the learning, and so if you are actually in the loop and you are learning more and more about the domain model, of course, over a period of time, incompleteness reduces. But these are the things that you need to think of in terms of just handling the current incompleteness. Okay, so what I'm going to do is look at these pieces in the context of preferences and dynamics. Again, this is like a reasonably large body of work, but we're just going to spend 30 minutes talking about these because of the time limitations here. And then so my interest is to sort of make you think of how planning changes in the context of incomplete models and tell you what sort of techniques are available. Okay, so in terms of preferences are like, what should the plan satisfy? Okay, normally you talk about goals, and in the classical model, the assumption is that the goals that the plan is supposed to satisfy are given to you as part of the specification, and every plan that reaches those goal states is equally good. There is no difference between multiple different plans, okay, which all reach the same goal. So, for example, if I say find me a travel plan to come to Austin from Phoenix, a plan which involves a flight is just as good as a plan that involves a little bit of hiking, a little bit of basically hitchhiking, and a little bit of running around and finally reaching Austin, because all of them reach Austin. Okay, so if there is no basically, if the assumption is that all the preferences are satisfied, and if no additional information is available, then you just assume all plans that reach the goal state are equally good. Okay, now if you have human in the loop, then essentially you do care about different preferences that may be implicit. Okay, so the question, of course, is this is just sort of to change your mindset a little bit. This is sort of off-the-wall example. So when you go to a search engine, for example, and ask a query, in particular, I think the most interesting query in the world is my last name, and then I check what is involved, what are the solutions. So here, this is from some time back. So obviously, it gives a large number of my pages. This is my page. This is my page. Then it also starts giving pages corresponding to other users. Okay. Now, why is that? Why is that a reasonable thing to do? Because again, in search engines, the query is underspecified. On one hand, you're saying anything that has these keywords is an answer, but on the other hand, you get to yell at the search engine saying, that's not what I meant. I really meant something more than what I asked you to produce to me. Again, implicit preferences. And the way Google and search engines handle this is by diversifying the results. So if you don't know who the user is, hedge your bets and essentially consider a diverse set of results that's more likely to satisfy a bunch of them. If I'm logged in, then actually Google does show me mostly my results. If I'm not logged in, it tends to show a diverse set of results that have the word company in them. Okay, which is basically what you will have to do if you are doing planning with partial preferences, when the preferences are basically unknown. Okay, so when the preferences are unknown, then we will be considering plans that are satisfying the goal but are as far away from each other as possible. In general, the notion of diversification is all the results, in the case of search engines, is all the results that reach, that basically have the keywords but they are dissimilar from each other. That's the idea. And the same thing we will do here. To diversify plans, you need to talk about distance metrics over plans. How are two different plans? How do you say how far is one plan from another plan when both of them are satisfying the same set of goals? So that's something that we need to talk about. We need to generate distance measures, and there's some work on that we've done. When basically you don't have any preference information. Okay, completely unknown preferences. Sometimes you have partially known preferences. So an example would be, you might be interested in making travel plans, and you kind of know that the relevant metrics on a plan are the make span, that is how long the plan takes, and the cost, which is how far costly the ticket is, but you may not know which is the way the user puts those two things together. So this is truly a multi-objective optimization. If you can combine the two objectives into a single objective, then it becomes a known preference, because then you can use any existing optimizing planners to find the problem. So in this particular case, if you don't know how the user is combining them, in essence, that would be a partial preference problem, where what we would try to do is essentially look for the Pareto set of solutions. In the multi-objective optimization, you can talk about non-dominated solutions. It's just that the Pareto set can be too large. Then you will start talking about what is the best way to find K most distinct Pareto set solutions. So once again, here too you're trying to find K solutions, except here the K solutions are farthest from each other. Here the K solutions are on the Pareto frontier and farthest from each other. So that's basically the technical background on using the preference incompleteness. So a little bit more details on this. So for example, for the distance metrics for the plan diversification, we can actually define distances on the plans in terms of the states that they visit. As you can imagine, you can define them in terms of the actions, in terms of the causal links, and in fact we experimented with diversification metric, distance metrics on each of these, and talked about how to generate K-distinct plans using existing planners. In fact, there is a paper here in AAAI where somebody, I think Robert Goldman, has actually looked at yet another distance metric over the plans, which is not, so in addition to the ones that we have looked at. So again, in general, you're talking about distance metrics over plans. This is something that you don't talk about when you just say, I have to just generate one plan. So that's what you need to care about in terms of diverse plan generation. And then once you develop the distance metrics, in fact, you can actually adopt the existing planners to generate K plans that are most distant from each other. So in this particular case, we were actually using LPG, which is a local search-based classical planner, and then we were just basically trying to make more and more plans that are farthest from each other according to the distance metric. So once you know what you need to do, then you can actually adopt the existing planning technology. That's the idea. Now, when you have, that's for the unknown case, when you have partially known preferences, as I mentioned, so you may have, for example, the knowledge that the plan preference of the user is a function of the time and cost, but you may not know exactly how they are combined. Okay, so in this particular case, if I make the assumption that they combined in some convex combination with W and 1 minus W, I may actually only know the distribution over W, but don't know the exact value of W. And if I don't know anything about W, I can just assume it's uniform distribution. That would be the maximum of it. So the real question is, if the W is unknown, but the believed distribution of W is known, then can I talk about what are the best K plans that I present to the user? Again, just since we are talking about this from the point of plan generation, remember that this is in a bigger loop where there's a human and you're trying to show the plans to the human. Okay, and then you're basically either going in the earlier case, you're showing K diverse plans. Here you're showing K diverse plans that are somehow more relevant to the measures that the user is interested in this particular case, make span and plan. Okay, so in this particular case, this becomes an actual multi-objective optimization problem. So you happen to know the objectives of the optimization, but if you have multi-objective optimization, you have a Pareto set, and the Pareto sets can be very large. So the question would be, basically you can use a normal existing planner, off-the-shelf classical planners, to come up with every point on this on the Pareto set. Either brute force or smarter techniques. But there are two real problems. One is computational, which is computing the full Pareto set of plans is quite costly. Remember, just finding one plan is space complete. Okay. The second is comprehensional. If you give the entire Pareto set to the user, they are probably going to say, I have no idea what you want me to do with these many plans. Okay. So presumably you want to provide options that sort of differ in qualitatively interesting ways. So once again, the solution here is return k representative plans from the Pareto set. Now the question, of course, is how do you define the representative and how do you generate the representative set efficiently? And that is something that, again, we looked at in this particular case. And so what we did, again, I would not go into the technical details right now because of the time, but in essence, intuitively what happens is, depending on the distribution, so we use something called the, ICP measure, which is the integrated convex preference measure, to kind of evaluate a set of plans, compare it to another set of plans. So if I have to give you only 3 plans, if I have this 3 set and this other 3 set, which is better from the point of view of they standing out from each other? And so the idea would be that the answer depends, the ICP essentially says that the answer depends on the current distribution that you know of the W, the weight. Okay? If you think the weight is completely uniformly distributed, then if you have a Pareto set like this, then probably this 3 set is the best one that you can give. Okay? If on the other hand, if you think the weight is actually sort of much more likely to be around 0.5 with much lower probability after 0.5, then you are better off giving this 3 set as the 3 most likely diverse plans from which the user would pick what they're interested in. Okay? So that's the idea of figuring. So you wind up having a measure for comparing 2 sets of plans, not a single plan, but 2 k-size sets of plans. And then once I have that, the solution approaches would be, for example, you can sample k different values of W from this distribution and find the optimal plan for each of those values. That's one idea. The other idea is actually to drive the search. Those of you who heard the heuristic planning tutorial in the morning, you can come up with heuristics that drive the search towards plans that would be essentially optimizing the ICP measure. Okay, and then of course you can combine both, and then it turns out actually that the hybrid methods actually do quite well. But I'm more interested in sort of making sure that you get the idea of what kinds of techniques are needed to generate this sort of diverse plans. Okay. So the other thing that just as I mentioned, although I'm not going to talk much about learning, in fact, in this kind of a scenario, what would learning mean? Learning would actually mean getting a better posterior estimate of the distribution on W. So you may have started with this, and you may have generated these 3 plans and shown to the user, and based on what plans the user picked, you actually have examples from which you can learn to improve the posterior distribution. And so later on, as time goes on, you can actually give diverse plans that are more likely to be relevant to the user than before. Okay, so that's how learning will enter here. Okay, so this part is about preferences. The other part I'm going to talk a little about is incomplete dynamics. So in the context of planning, dynamics is the action models, okay, the preconditions and effects and so on. So in the previous case, we assumed that the planner knows the complete model of the dynamics. It just didn't know the preferences. So it's trying to figure out what would be the plan to show. But all plans will execute. Okay? When the domain model is itself incomplete, the plan that the planner makes may not actually execute. Okay? And that's because the planner doesn't know the preconditions and effects of the model. This is actually what the trains program was basically talking about, that the planner may not know the full domain model, and it might actually wind up needing the human cell. So in the case of domain model incompleteness, it becomes a big question as to how incomplete is the domain model. So for example, for the preferences we talked about, no preference knowledge is available versus partial preference knowledge is available. In the context of dynamics too, we can talk about no model at all is available, or full model is available. So this is where classical planning has been. No model is available is essentially, actually there is no planning model whatsoever, and so the only human knows where the plan is going. The planner has no actual clue where the plan is going. Now in the examples that we have looked at in the beginning of the tutorial, the crowdsourced planning falls on this direction, because planners probably won't know that much at all about what sort of plans would be good city visiting plans. Okay. Whereas I could also have full models which are sort of kind of less than full in the sense that some of the actions don't have full information about their preconditions and effects. So I would actually for this tutorial we'll mostly talk about, for this next 15 minutes, I'll talk about how to handle models that are approximate. That is, they're almost complete, but there is some information that's missing about the preconditions and effects of some of the actions. Okay, and how do you handle that? So now that's kind of, this basically is Donald Rumsfeld, who was the defense secretary at one time, and he had this great philosophical saying, one of which basically goes saying that there are known unknowns, that is to say there are things that we now know, but that we don't know. So what that basically means is you could have domain models that the user provides saying here are the preconditions and effects of all the actions, but here are some possible preconditions and effects, and I'm not completely sure that they are actually required preconditions for the action, and I'm not completely sure that these are required effects of the action. Okay, so you may start with, so the question that I'm trying to answer here is, when you start having approximate models which are incomplete, I can't just give you the model and say it's incomplete, I have to give a little more than that. One idea would be that I showed you the sources of incompleteness. Here are the actions for which some preconditions are possibly holding and other preconditions are definitely holding. Okay? And if I have possible preconditions and possible effects, then what happens actually is, so you have a scenario like this, where this action has precondition P1 and effects P3 and P4 that are guaranteed. Okay, except these P3, P1, P2, this may be a possible precondition and these may be possible effects. Okay, what that means is that in some cases, in the real world, action A might actually need P3 as a precondition, or it might not. The only difference is this is not stochastic. Either all the time this action requires P3 as a precondition, or all the time it doesn't require P3 as a precondition. You just don't know which one it is. So there is some kind of hidden variable which is deciding whether P3 is a precondition or not. So this is a reasonable way to model, and I will actually tell you in a minute that even if you don't have anybody annotating these, there is actually a way of making up this information. Okay, but if I have this sort of information, then if I have two actions, if I have just one action with one possible precondition, then that possible precondition can be either true or false. So I really have two possible action models. And then if I have 10 actions with one precondition which is possible, each of them, then I have 2 power 10 possible models. Okay. Now the question of course is, which of them is the true model? One of them is the true model, and what you're trying to do when you're trying to do planning is to make a plan that sort of works in many of these possible models. Okay. So the solution concept for this scenario winds up becoming, we want to make candidate plans that work in as many of the candidate models as possible. And you can also provide probabilistic semantics for this if you happen to have likelihood of these possible preconditions. And you can talk about plans that are robust in the sense that they will work probabilistically work in the most number of candidate models that are possible given the incomplete dynamics. Okay. Now, one thing that I want to mention is that if to the extent you do not quite believe that users are going to sit down and write what are the missing preconditions and what are the missing effects, okay, which is a reasonable question, because how come if you are lazy enough not to know what the complete model is, how come you know the limits to your knowledge and you sit down and write? It turns out that if I actually find a set of planning techniques to handle this kind of models, then here is another approach which can actually piggyback on that. So for example, oftentimes the you might be able to get an incomplete model and a set of cases, set of past plans that actually worked. Now when that happens, I can do the following thing. I can basically start by saying for every action model, I'll assume that every other literal in the domain is a possible precondition as well as a possible effect. I just assume this vacuously. This doesn't require anybody to tell me anything. And then once I put these in, then if I know that there's a bunch of plans that definitely work, every plan that works puts constraints on what can be a possible precondition, what can be a possible effect. So in fact, as I get more and more plans, I'll actually know more and more about what are really possible preconditions effects, and that winds up being a way of understanding that really this is not a particularly hard to achieve information. Okay. So now the question, of course, is what do you do when you have this kind of models? That is, you have possible preconditions, possible effects, and as I said, you want to generate plans that work in as many of the candidate models as possible, and there are like two ways of handling that problem. First of all, one thing to notice is if I were to give you a plan in this domain, in this kind of a formulation, then you need to ask yourself how many models is this plan correct. Okay, normally in classical planning, if I give you a plan, you can write a proof structure saying, notice that the first action's preconditions are satisfied in the initial state, and then its effects are being used by another action whose effects are being given to the final goal state. Those are called the causal proof constraints. You can write those causal proof constraints as a set of SAT clauses. Okay, now what you're doing is, previously we just have to see whether the SAT clause is a solution. Now you want to see how many solutions are there for these SAT clauses, because you have multiple models and you essentially have to count the number of models. So right now, finding the robustness of a plan involves weighted model counting. Okay. The next thing, of course, is if I have a way of assessing the robustness, my interest is to generate a plan that has high robustness. And to do that, we actually can look at two possible approaches. One is realize that these possible preconditions can be thought of essentially as known preconditions which depend on some hidden variable in the initial state. And if that is the case, then it becomes what's known as a conformant planning problem. That is a planning problem where the domain model is known, only the initial state is not known. Okay? And there is probabilistic, at the initial state, there is a probabilistic distribution available. And so you can compile the incomplete model with complete world state into complete model plus a plus a incomplete initial state. And then that you can just use conformant planners. Okay? And that's one idea for solving these kinds of problems. And we had a paper on that. There's a paper on this in like NIPS like 2 years back. And another way of solving the same kind of a problem is more directly is to actually sort of use heuristics which actually assess the robustness of the remaining plan. So the assumption here is I'm generating a plan, I have come up to this much, so I've started from initial state to some intermediate state, I know the set of actions in that plan. So I know, for example, how to compute assess the robustness of that piece of the plan, but then I don't yet know how to go from here to the goal state. Now I can use a delete relaxation style heuristics to compute a relaxed or approximate plan from here to here. And now then I can essentially say that I can talk about assessing the robustness of this total plan, where this part of it is really an approximate plan. It's basically ignoring some of the delete information. And then of course, even here, assessing the robustness becomes a hard problem because, as I said, robustness is weighted model counting, which is an NP-complete problem. So that means the heuristic computation itself is becoming NP-complete. There's a paper in last year in ICAPS, one of my students basically showed that one nice thing about the relaxed plans is that these constraints for computing the weighted model, they all wind up having a special structure. They only have positive literals. And when there are only positive literals, it turns out that you can come up with easy upper and lower bounds for the number of models. And then you can use those upper and lower bounds to guide the heuristic search. So coming up a few levels, basically what we have done here is to first motivate that there actually can be incomplete models when you have humans are in the loop with the planners. And then when you have incomplete models, it's a non-trivial task to actually develop planners which will handle those kinds of incomplete models. And I looked at incomplete preferences as well as, in this case, incomplete dynamics. And I also mentioned that although my discussion on the incomplete dynamics looked at annotations about possible preconditions and effects, and it is reasonable to ask where do you get these annotations if it is actually incomplete. You probably would agree that many a time you would have known completely correct, known plans that have worked in the past, and you also know partial models, okay? And so these partial models can actually be essentially be extended with vacuous possible preconditions and effects, because everything can be a possible precondition effect. And then these cases which have worked in the past will actually add additional constraints on the classless, okay? So that way you can still use this method for developing robust plans. So I'm going to stop there, again with the point that before we came up to the incomplete preferences and dynamics, Karthik was mostly talking about planning techniques that exist right now and just adopting them. And this part we wound up having to actually develop new planning techniques, including new solution concepts. What it means to be a plan for a problem changed when we had incomplete preferences, because a solution is a set of diverse plans. And similarly, what it means to be a plan for a domain incomplete dynamics has also changed, because that needs to be a robust plan. Okay. Thankfully, so that basically completes the discussion on the decision support, and Karthik is going to come back to talk about communication, and then sort of putting so basically we gave partial solutions, at least the ones that exist right now, for interpretation, decision support, and here we're talking about communication. And then he will talk also about how we put together these solutions in two of the examples that we looked at, which are in two different parts of the spectrum. Okay?
Alright. Okay, so that's the last changeover of speaker, I promise. So we are stuck with me till the end of the tutorial. So, okay, so we talked about two challenges so far. We talked about interpretation, and then we talked about three different problems to be solved under decision support. What I'm going to talk about now for roughly the next half hour or so is, or a little less than the next half hour, is this challenge of communication. Okay, so the idea here is that interpretation was where the planner is trying to figure out what knowledge the human in the loop is actually, trying to figure out knowledge from the humans in the loop. Okay, decision support was sort of the opposite problem, which is basically once the planner has context, once it has knowledge about the scenario, it's trying to figure out what do you do in order to support the team planning process or the team plan. All right. Now, communication actually has aspects of both. It has aspects of interpretation as well as decision support, okay? And we'll see that. So, in particular, the two kinds of communication that I'm going to talk about. First, I'm going to talk about reactive communication, okay? So, whether it's a planner or a crowdsourcing system, the planner is acting reactively, okay? So what do you do when something goes wrong? You can offer excuses, you can offer explanations, and these are things that humans expect, right? Because when you think about how humans interact with each other, they expect that when something goes wrong, they will be provided either an excuse or an explanation, whatever it is, okay? So the first part of this is a reactive way of dealing with communication, okay? The second is a theory of dealing with communication in a proactive manner, okay? So if there are things that the planner doesn't know how to do, okay, or if there are things that the agent cannot fulfill because of a certain thing, how does the planner actually make a plan in order to proactively ask for help, for example? Okay, so those are the two things I'm going to talk about under the umbrella of communication. So the first work that I'm going to highlight here is this work on coming up with good excuses. This was presented back in ICAPS in 2010, And the idea here basically was, again, going back to the discussion about replanning that I was talking about back in the decision support section, right? There are all sorts of failures that can happen in the world, right? And particularly when you're talking about human-in-the-loop systems, for example, human-robot teaming, you can have both planning failures as well as execution failures, right? So planning time failures include your knowledge being just wrong, okay? So your planner might have an incorrect notion of the domain model, of the dynamics of the world, right? As Rao was saying, you might have incomplete and sometimes incorrect knowledge, right? You might also have missing resources that you either didn't model or you just modeled them wrongly, and sometimes the task might just be unsolvable, right? So your planner might be given a task that just doesn't have any solution. So those are planning time failures. There are also execution failures, obviously, which is what we talked about, for example, replanning, continual planning, coming up with a new plan when there is an execution time failure. Alright? So there are all these kinds of failures in systems that incorporate planners as one of the main actors. Okay? Now, one way of dealing with these, like I said, is a reactive way, okay, which is you can offer excuses. So in this context, you can think of an excuse as a counterfactual statement about the problem that you're trying to solve. Okay? So something like the robot says, if the door was unlocked, then I can figure out a plan to bring you your coffee and morning newspaper. Okay? So here the excuse is basically the door is not unlocked, hence I cannot do this for you. Okay? Now, in this particular paper, they use a slightly more formal notion of an excuse. Okay? So to them, an excuse is basically a changed version of the initial state of the planning problem. Okay? So the idea is basically, if you think of an initial state for a planning problem, it's nothing but a set of fluid values. Okay? And what they say is that these fluid values that can now be changed. Okay? So you have change operators that you can apply to the initial state to change it. And obviously they try to exclude certain things which would make it a trivial problem, it would make it a trivial solution. So for example, you cannot make any of the goal atoms immediately true in the initial state, okay? So that's just, that's not an excuse anymore, that's just you're changing the initial state to the goal. And similarly, you cannot change a fluid that directly contributes to the goal formula, okay? So there are certain restrictions on what an excuse can be, but this is the definition of excuse as provided in this work. And example over here, so suppose this is your simple toy problem, okay? You have a robot that is out here in this, in this scenario, and what you want to do is you want to basically tell the robot to go to room 1, okay? So there are some possible excuses that we come up with. So for example, why did you not open the door to room 1? Because I don't have, or why did you not open the door to room 2? Because I don't have the key to room 2, so it has key 1. Okay? Or another possible excuse when you ask the question, why did you not get the key yourself, right? Is the key might be inside here, and it says because door 2 is not open. Okay? So the excuse is to open door 2 essentially. Okay? Another possible excuse is why couldn't you open door 2 on your own? Because I had no way of opening the door. I didn't have a key. Okay? So these are all possible excuses that could be generated, and the point of this work was basically how do you generate these excuses? How do you make it a planning problem? The generation of excuses, how do you turn that, how do you compile that into a planning problem, into a problem that a planner can solve, okay? So, one definition here is that of a good excuse, and this builds up to the notion of a perfect excuse, okay? So a good excuse is an excuse that cannot be regressed to any other excuse, okay? So when you have things like static facts, okay? Static facts are things like key in room 1, okay? That's not going to be regressed to something else. So that's a good excuse. And then you have this notion building on top of that of perfect excuses, okay? So this happens when you start associating costs with excuses, okay? Because so far, in the discussion we've had so far, we've thought of excuses basically as change operators, as change actions, right? So obviously there must be many of these actions. And if you start associating costs with these, right? Because obviously not all excuses are created equal, so to say, right? Because adding a new key versus adding a new door, clearly those two are different in some respect. And you can model that difference by maybe assigning a different cost to them, right? So dreaming up a new key is significantly less cost than dreaming up a new door, perhaps. Okay, maybe it's the other way around, depends on your scenario, right? But you can associate costs with these, and what they say is basically a good excuse with minimal costs is known as a perfect excuse. Okay, this is just nomenclature, it's just a terminology. Okay, and the crux of this work is essentially that they reduce the problem of finding excuses to a planning problem, to a plan generation problem. Okay, so they're compiling the problem of finding excuses for your planning problem into yet another planning problem. Okay, so basically what they do is they introduce this notion of change actions. Okay, that can modify your initial state at will. Okay, and remember, because there's a cost associated with changing the initial state, depending on which fluent you're changing, there's going to be different costs associated with each one of these change operators, depending on what it is you're changing. Are you dreaming up a new door? Are you dreaming up a new key? Maybe you're just dreaming up that the robot is in a new location, okay, and so on. And you basically partition the plan generation process into two phases, and only in the initial phase you allow this application of this change action, okay. And basically, that's what they do. They compile this excuse generation problem into a planning problem. So, I'm not going to go into more details about this work. You can look this up. This is a 2010 paper. But similar to this, so in this paper they were basically talking about reactive ways of dealing with plan failures, of communicating with humans. So specifically they're communicating excuses. There's been further lead-on work. So in 2011, for example, Shirin Sorabi and others, they basically came up with this work of offering explanations. Okay, so now in this case, in addition to something going wrong, maybe you also have certain observations that you happen to see. Okay, that your planner happened to get. Okay, so for example, if these are the observations that you saw, what are possible explanations for this kind of thing? Okay, where in this case the salient thing to see is that you started your car, you drove from home to work, you got off the car, and then there's very low temperature that day. Okay, then in the evening perhaps you came out of work, you started your car again, but the engine won't start. The engine is off. Okay, but your radio actually turns on. If you turn on the radio turns on. These are observations at the bottom. Okay. What could possibly explain this sequence? Okay, and you will start seeing that this looks suspiciously familiar, right? Because this looks close to the plan recognition thing that we were talking about in the interpretation section, which is why I said that communication has aspects of both interpretation as well as decision support baked into it. Okay, so in this case, instead of just offering an excuse, instead of just saying here's why maybe the engine didn't turn off, they're trying to come up with more of an explanation for what could explain this sequence of observations at the bottom that you're seeing. Okay, and again, like I said, I'm not going to go into details of this for lack of time, but you can look up this paper where they talk about preferences, generating preferences, okay, using preferences to generate these explanations. So some explanations are better than certain other explanations. So it's basically a generalization of this notion of cost over excuses. Okay, now you basically have preferences over explanations, and you're trying to choose the most preferred explanation given a sequence of observations. All right. So these two papers that I talked about, these two